Hello, my name is Mohamed Kassem. I am the co-founder and CTO of a company called eFabless. And I will present today, I'll talk a little bit about what we've done around the openness or the democratizations, the word that's being used all the time, but I believe it's being used here appropriately, of the custom ASIC. And we'll show you some history of that and some of the things we've done and some of the things that I think we'd like to do together. So my background is analog mixed signal circuit design, and I used to work at Texas Instruments in the wireless group until 2011. And I have chips in many of the phones that can, whether you can like them or not, basically you could hate the phones, but now you know the reason. For Nokia phones, a lot of them. That was when Nokia was Nokia, and then more recently, where I was towards my departure, the Motorola and Amazon devices. There was a device called OMAP, and I was responsible for all the analog mixed signal on it. So I also, and pretty much one of the reasons I evolved to become who I am is tinkering. So I blew up things until today, but long time ago, that's how it started when I was a kid. I do have, I open devices sometimes destructively and just to destroy them and see what's going on because I couldn't tear them down appropriately or gracefully rather, and end up buying another one just to use. Or actually to understand what's going on in these devices and analyze how we can proceed further if we wanted to have an open source custom ASIC solution for some of these devices. So we believe, or I believe in the world needs custom ASICs. And historically, the custom ASIC is cornered in the world of high capital. And it's actually, a lot of it was driven by the smartphone. So the size and the power requirements and the performance requirements and the leakage and battery life have driven the world into designing things in different ways. Of course, the cost as well. And I have witnessed that at Texas Instruments myself because we would, every 2 years, we have to come up with a new chip for the next generation of the phones with a different technology node from 180 nanometer in the year 2000 all the way to where I left. It was 20 nanometer in 2011. And there are reasons for that. Obviously, some of that may be clear from the Intel life cycle of kind of a Moore's law in reduction of the size of the transistor and the packing density. So the bottom line is the phone, in my opinion, drove the low power need for compute. Today, we're coming back into the world of so-called Internet of Things, which a word or expression was used back in 2010 as well. But the way I see it is we're getting that, after integrating everything in the phone, we're dialing back and saying, well, let's chop it up and make it a bunch of things with different types of sensors in these devices around our life. So I would say maybe one of the best options are maybe an overkill of an IoT device, if you can shrink that phone with a wand to a dot and just becomes with its cameras and compute and power and communication available. So there is, and if you haven't seen it already, there will be people sometimes call it smart, enabling smart devices. Some people call it just automation, but it is exploding. And you look around, and then the term that's used, or I'd like to use, is that many of the devices are being converted to be citizens of the internet, and that means you give them the connection and the smartness to do so. The custom ASIC will be useful in enabling true customization of a lot of products. So today, living with the, thank you very much. Living with the standard devices, whether it's ASSPs, kind of at the closest part of it, or is something we have to live with, because we have to live with it, and the cost of choosing to customize is prohibitive. So it's out of the question. Especially if it's a low volume product, something like on the right hand of the slide here, and so-called long tail, and probably seen that expression many times. And there will the ability to customize or optimize the software and hardware together at the ASIC level or at the electronics level has not been available in the low volume world. It's only been available on the high volume, and you can see it from companies like Apple has been driving that many years, and then more recently, by the way, they always did their silicon, except that they chose to change the cores into they always did their silicon for the phones, so versus the laptops. But the reason for that is that they wanted to have a combination of optimized hardware and software together, regardless of versus the other approach, which general purpose compute, increase speeds and performance, and then you put a same stack of software on it. So there will be the need for the right size compute and power. And I make this a big statement. And again, when you're sitting down when we were doing the smartphone discussions about the chips, it was all spreadsheets about what architectures and what cost and power performance, and then you manually kind of people with a bunch of people sitting around looking at, okay, we need to do this because we're going to optimize, get the same optimization, but for the application of the phone, which was driven a lot with the video and multimedia and gaming, in a sense, actually. So, and we need, in order to do that, one or two ways to generate these ASICs. It's either designers that know how to do it, or automation. I think the world's going to be a combination, because I think design in electronics or the hardware, or design in general, is an art, and there will be some things will be improved through automation for productivity reasons, but the designers will believe that there needs to be a significant increase, which means, we need to change how it's being done. And why do we care? And some people, as much as as many years I've been in the chip development world, if you ask me that question, I wouldn't just give you these 4 bullets like this, because if you're inside that world, it's just natural. So there are many aspects or many ways to look at it, and they're just a subset, and they don't apply in all cases. So it's not going to be always the cost reduction or the performance or the size, or the intellectual property. One thing I call is that when you design hardware from scratch, like even a certain device in your hand, any device, product, for the lack of the different devices, I'm just going to hold the phone again, or something like the Oura Ring, the smart ring. The knowing that you can customize the electronics gives you more flexibility in the form factor design. So, and that actually, knowing that coming in, it allows you to make better decisions on the form factor or the power or the overall design of a product, if you know that this is a tool in your bag, you can actually do that, versus living with the existing Lego pieces, which they have certain sizes. They may not be fit to be put in one place. And a lot of people do the ASIC solution for something like what's on the slide here, which is just replacement of some or old solutions that logic doesn't exist, which is still a big deal actually. And it's not necessarily just, I'm not talking here about today in the US, for example, this is worldwide. So what we wanted to do, or we want to do together, is to simplify the process and make it available to everyone. And that gets me to a point where if people looked at the world before the app stores, whether it's Apple, the Apple App Store or the Play Store from Google or others, in order to build software product and sell it, you come up with an idea and you want to start putting it as a product and sell it. So just imagine what do you need to do. So in the best case scenario, you have the technical capability to do it all, and then now you need to find a customer. Now you need to find the time to do it, and who's paying for it, et cetera, et cetera. So what happened with the app stores, they really provided certain pieces that made that explode, and explode to millions, and beyond, thousands or hundreds of thousands. And actually, just maybe the numbers here, if you calculate them right, I may be off big time, but you can see the difference after the app stores, you can see how many, final product in form of apps show up. And then also, so that primarily what happened is the SDKs, or they made a structured, standardized approach to do that with a certain minimum level of quality. That's very important. And the second is there is a business process, so the developers can follow and go through it. And the third is connecting to customers and knowing what the market actually needs. Now, in the app stores, it's a little bit tricky because most people, they think and guess what the market needs, and then because you can actually put it in the marketplace, you see what happens. So I always give the example of Angry Birds, just as a, it's a theoretical thing. I made it up, but actually it's a good way to look at it. Is that if you imagine the developers of Angry Birds, maybe some is here, I don't know, standing in front of an investor saying, I want to develop this game with a slingshot shooting birds. And it's going to have on the other end 2 movies, Angry Birds 1 and 2, and it's going to be like massive household name. Nobody knows what would have happened, but I'm claiming that it would have been hard to make the case for investment for this. So, but because of the app stores and the capability that exists, they just do it. They just start to do it, put it, and then have the market judge it. And I think this is the same approach will apply to hardware if we do it right, whether it's based on custom ASIC or not. So we can do the same. We believe we can do the same for the design, and we can extend it to a large number of people as well. So if for those of you who are familiar with just the high level without getting into the very detail, is that there are a lot of shackles and a lot of barriers. One of them is money, but actually, even if you have it, it's hard to get the rest. So you have to get software from software companies. You have to get access to the technology information from a foundry. And even if you get that, maybe the money is going to help you for making the manufacturing possible for you to try something. Let alone the NDAs, which are very interesting because you don't sign an NDA with someone who you don't know or you don't know how to sue. That's how the companies look at it. So it's very hard to get that signed and done, no matter, even if you sign it. So in the chip world, if I wanted to apply the same example of an SDK in the software, I'll have to at least look at these 6 items here. So I want to know, what's out there, what people need. I don't, for a given chip design or a system, I don't have all the knowledge myself, one person, so probably need other people. And they need blocks. So if you're building a chip, you're starting not from scratch. So you're gonna, if you're familiar with the process, you're gonna find that if you need even a peripheral like SPI, that's an IP, that's something you need to acquire, it has cost. Example also ARM IP or ARM cores. The EDA tools, the so-called the PDK, and the PDK, I'm just, without having any graphical illustration, it's basically a bunch of models that represent what can be manufactured. So it's a way to have the designer to know in their hand what's possible to manufacture. So you don't do something that's not manufacturable. And it's represented in a bunch of models and files that gets work along with the EDA tools. And then after doing all that, then the manufacturing itself costs money. And if you manufacture it, you want to test it. So on the right-hand side of this slide, I say useful. I actually mean to end up in a product. So that's a very important piece versus a test chip for tinkering, which is a great thing to do. But as I go through and move forward, you're gonna find that I vouch a lot for that because it lifts up the ecosystem big time. There are examples of partial solutions that are around the world. So people will say, I want to go create shuttles or aggregation, and there are systems that would have less of a criteria or to have you sign an NDA, so they exist, but they don't provide a solution. Most of them, they come with the shackles of academic purposes. So if you want to do this, and even if you're in a university, and then you have access to all this, and actually this is a phenomenon that I see with professors, not all of them, but just call it 20% of the professors that I talk to, they say, I have everything. Well, so this is the effect of, you fly F-16s, you get trained on them, and then you get out of school, there are no F-16s out there, you can't get them, okay? You have to go work somewhere else, So it's just sad to be, I think it's not sad, it's not consistent with the progress of the industry to have this captive to this date, or to at least 3 years ago until we all started to be captive within a certain subset of boundaries, or I'm going to say subset of people, but especially within boundaries of access, money, or otherwise. So when we started, I wanted to solve the problems one by one, but I really, when I started, I did focus on the EDA aspect. I said, first, let's check to see if there are software out there that actually can people do anything useful with it, or good. I was comfortable with that because when I worked at TI, believe it or not, so because my team, we were working on we were the design team that works on any technology first time. So everything is inaccurate. Simulation models are not good enough. Tools are, you have to hack them a lot. So, let's say I didn't think that the open source software that's out there is any different. Actually, I thought it's maybe better because I can actually talk to other people with the freedom of openness. So I literally traveled around the world, identified first who did something successful with a simulator, a router, synthesizer, or whatever. So I went and basically told them, let's get together and do something to make real chips and real products. There's a lot of skepticism that eventually worked out. Now, if you notice the small text here, which is something that I'm not intended for you to read it right here, but there is a word open source is just all over the place. And that's actually where we're going to go. So as I mentioned, I looked around, like literally, I had a collaborator with me we had this massive table of matrix of what tools exist and what they can or cannot do, and actually trying them. So that was the start. And you can give these tools to anyone, to anywhere, without the permission of anyone. and anybody has an idea, they can use them right away. And I applied that on analog and digital, and the reason I'm putting this specifically here because there is sometimes perception that the analog is actually less served. It is less served in terms of quality of or user experience, but it is there. So it's actually, as a matter of fact, it's easier to work with it in open source. So this is kind of obvious. Why should be open source? But it's hard to actually do it in the semiconductor world to actually make that case. Because it's actually, I'll say this, and I'd like to say it publicly, and I keep saying it, is that the semiconductor industry is the industry that least benefited from its own progress. So we increased the compute capabilities and the ability to, the computers have evolved significantly, but the productivity and the ability to generate chips and the way we do create chips haven't changed for decades. So, and I can challenge that, at the bigger picture level versus just a specific design. So we all know that. So when we did this, I started saying, well, let's go do some ASICs with the tools first to take some risk. And we did a few of them. So this was just a few analog blocks put together with this SPI around them. And it was done with open source tools. Slide changed. Oh, yeah. This is a second chip. It's actually one of the big transformative chips in the whole discussion that's come forward. It's a RISC-V microcontroller. And again, the only thing that's actually two things are open source here at a high level. The core, which was a RISC-V core. And then the second is the actual chip, the top level. But because of the time when we did it, there were no open source analog blocks. So we just had to live with it. This is another version of that. So they were actually intended to actually blaze the trail and say, okay, it's possible. We had, once we did this, we had actually, because if it's an open source chip, the security aspect of that appeared. I wasn't actually very privy to that, and I learned it over time. Is that, so we got approached by NEC Israel, and their approach was like, they found this, you guys have the only open source actual chip that we can use for as a root of trust to verify. Now, obviously, to verify that doesn't have Trojans. There are holes in that argument because you can verify the chip design or code that doesn't have any Trojans, but by the time it gets manufactured, you need to trace out the supply chain all the way to know that's actually clean. But in that case, at that time, that was the first chip, so they used it as a coprocessor to do that. And their case was, it's a small chip, inspectable, I can prove that it's clean, and I know what's in it exactly. So we designed these 4 chips with open source tools, and with no intervention from or use for any. This was actually an important thing, is that we needed to stay clear of any contamination because to keep things clean. Second thing, I mentioned the PDK. The PDK is it's the library. Call it the library for now. If you compare to the FPGA world, it's you have the software that comes with the FPGA plus the library, the target library, and the FPGA. So the PDK is similar thing for the foundry. So they're in a very interesting twist of events. We partnered with Google and Skywater, the foundry. And Skywater, actually, for the background, it is the foundry that is a spin-off of Cypress. So Cypress is products that are PSOC specifically, for example. If you're familiar with it, they were manufactured on Skywater, especially the Skywater 130 that's mentioned here. So the results of that led to another foundry to follow through, and Global Foundries, which actually created 2 things: a small foundry doing something, and a big foundry, the second largest in the world. So these were 2 score points, made other people question how come, anybody that comes later is going to be the third, and then the next one is going to be fourth. So the third one was the IHP from Germany. They did it on their own, and they saw the benefit of that. And the benefit is that more people will actually be able to design, and statistically speaking, that means more potential business. So I like to use the word viral here, because that's what happened when the PDK was published for the first time in June 2020. And this is, compared to other open source projects on GitHub, and you can tell the span here is about 7 years, but that's what happened in like less than a month. It's almost like the world was waiting for that statistically, the download aspect, of this typically take, tens over a year or maybe a month. It was happening at like 300 times a week, for 2 years. So it's a lot. And we get, a lot of people are assembled around it. And this would be an interesting community because the discussions are around the chip development in different aspects, chips or software related to it, or embedded hardware or compute. And I encourage everyone to go there because it's unique. If you're used to the NDA world of the chip development, you'll be shocked how much of that is actually no longer under NDA for these technologies. So the marketplace, and I won't press on that too much, but the objective, at least from a company like eFabless, was to reach to that level where you have everything you do, but also I want to give you ability to monetize that, because that's an important piece, and reach the market. And it's still in its start, so we're still working on that. And the goal for this would be something like this. It would be, the community would be able to develop what they think are good ideas, and they put them in the marketplace for the market to judge it, or the other way around, which is system companies that want to develop chips, they can do that either themselves or through the community. And I mean here community, I mean everybody that, whether individuals, universities, companies, big or small. So speaking of the SDK, so it's building a standard to build on. So we did, this was a part of the project we did with Google, is to build a baseline template chip that's available, and it has a standard interface in the middle that the designer just focuses on it. If you look at it this way, you don't start from scratch. Number two is that the knowledge required to develop something goes down. So you'll focus. I honestly think so. ESD, reliability, IOs, all these are things we have to expose the function of the thing we designed to the world. So you may actually have the perfect chip, but you screw up the ESD or the IOs, or it's not going to work. And it happened to us actually. But having that designed as a starter helps. And then we created a way to integrate that. And because we have an interface, standard interface, we can put a board attached to it. And then that board, you can actually plug it into USB and actually start with it. So it becomes, and I have that board, I'll pass it around, but this is the most recent version of it. But it actually helps to simplify the process, to start from a known point and work your way out of there. This chip actually is a RISC-V microcontroller by itself, a bare bone. It has a logic analyzer, it has some peripherals, and it works with an external flash. And everything in it is open source. This is the tools were open source, the PDK was open source, the entire design will be out there. And if you haven't seen that chip, if you go to GitHub, that link, one of the things that out of the program with Google and was, in order for these things to be successful, we needed to have some sort of reproducibility. So if it's just a design and thrown out there and you look at it, it's actually useless almost. But having the intermediate steps and the files and the documentation. So this was actually one important thing. So we put a standard structure for this. It's not perfect, but it led into people starting putting more information. And the working with the Google team was interesting because coming from the chip world, like the hardcore hardware, well, not hardware chip, specifically the chip, with the traditional development process, working with the Google team, the software guys that are very saying, okay, I don't know how to deal with the DRC or all that physical stuff. I just want it to work and it be tested with CI. Some really cool things that have never been applied on the chip development cycle. So it's very, very cool to actually have that knowledge diffusion coming both ways. So you end up with this, and you get a board, and this is actually a picture of the most recent board. We have two types of parts, packaging, CSP, and QFN. And one of the events, call it unfortunate or fortunate, we had a bug in the IOs in one of these chips. So actually, a lot of the designs became stuck in jail. So this, we came up with a way to understand. It's almost like playing with a key lock until you're able to unlock it. So we did this with software. So we had a Nucleo board from ST that actually would characterize the chip and would determine what tweaks we need to make in the software to make the IOs work. So we ended up being a tester. So we developed this board. So now not only can you just do it, you can test it. And then the white little daughter board or breakout board here, it was interesting because speaking of simplification, if I give you a bunch of parts on the CSP, that's not simple. If you really want to simplify it, depends on who you are, obviously, but or what you're passionate about. But if you really want to make it simple, you need to. So we gave both. So we ended up with the breakout boards and parts. Mostly on the left of this is actually just how the most recent testing process that we applied, just with the Vigilant, the 82s kits. And in this setup, I put a dedicated computer. This is running Python. It will just go through the chip functions and verifies them. This is one of the examples that was done with a Stanford student in a course, and which was possible because it was the time required to design was actually possible to fit within the course cycle rather than starting from scratch. These are, I'm just flashing them here to show, one of the new things that have been done here is the silicon validation. So typically there is verification dashboards and test benches. This one is jumped all the way to doing it with the setup that I just showed earlier, but it confirms that we have to do it to confirm that what we verified in simulation is validated. We did it in 2 different chips, 2 different foundries. So, and this is part of it to show that you have a baseline chip that's actually, if you have doubts about it, it's not good. So now we came to, after all this, abstraction of knowledge is important. And this is, again, doesn't exist, but I'm just using it for, I want to get to the right hand of the slide, okay? So now there's a flow, that software that takes from RTL Verilog to the GDS to that block, generates that. Well, if we go backwards a little bit, what can I do more? So we used different things to put in there to make it easily interfaceable to what people know. Now, first we started with that flow. It's an open source digital design flow back end. It will take you from the Verilog all the way to GDS. And usually you have to tweak it and do some configuration changes and so. But you ask, based on the discussion, can I use the comment from Tim Ansel here from Google? Again, I don't know what a DRC is. I don't know how to fix it. I don't care. I want it just to get done. And even if a bigger area or lower performance, So if you think this way, this is completely against the DNA of a semiconductor industry. You would actually enable, conservatively, I'll say 1,000x more people to do it, because it becomes like software compilation. And a part of that, actually thanks to the persistent interaction with Google, is that the bottom part of the chip here, which we call it the management area, this is the RISC-V core plus the peripherals. It was generated by through LiteX, and it's for those who don't know LiteX, it's the ability to actually through Python interface to write or configure or target different designs to different FPGAs. So we just added another target for ASIC, and it was interesting to actually make it work. And it's not fully flushed as something that's out of the box usable, but we've proven the concept, and some things are still work in progress, including this concept. One other way of abstraction, one of our community members, his name is Matt Van, created Tiny Tip Out, and that took it to a different level and said, okay, I don't want you to even do Verilog. I'm just going to give you a schematic editor on the top left, and you hook up a few things with a lot of restrictions, and you only have certain small area, or this area, and then I'm going to take this and stick it into 250 ways inside the big chip and multiplex them. So this way, actually, we have high school program that did that, and you end up with, and we started thinking it's going to be a high school, but after doing it, it's actually pretty cool to sit down for 2 hours and try something, whether it's your high school or not. So it became very appealing to many people, including myself. So there was in order to innovate, you need to keep tinkering and try and fail and learn. So there was a bigger issue here in that if I'm going to do this with silicon, it's a little hard. It costs money, and this is where the Google Open Silicon Prototyping Program came in place, and this was over 22. Google funded manufacturing of shuttles for using the environment or the tools that were available. With an interesting condition is that there's no judgment except that your design is clean, manufacturable. It's a lottery, and people get into it, and with the also restriction that it's open source. Everything is open source, which is a good restriction. So since we chose that, an example here is that one of the things we did is that since we fixed the tile size, this shot here is the mask, the full mask. So we divided that into the 42 slots. 2 of them, the gray ones, are gone to the foundry. But when the first shuttle was open, it was very quickly populated. Just in case you think about it, the first time it was like a little bit of if we open this to the party and say, okay, we're going to have ASIC design sitting inside this party, how many people will show up? You'd be nervous. So we got the first hint very quickly. And from companies, individuals, it was great. So to just see what's happening, and this is number 1 and number 2, and then you can see that people use it differently. So just as different designers do different things, and just for fun, after I got this, I just put them together and side by side. They're not the same aspect ratio, but it was manual sort in a sense. It's actually important to say that the simplification worked. So about many people, 60% were of the people on the doing designs were first time, coming from either software or the FPGA world, or chip designers that never did before, never had the chance. And about 1/3 identify as software developers. We did a couple of test chips in the beginning, and then if you see here, there's MPW 1 through 8, and then there's one, it's an MPW 0 for another foundry. So this process worked with growth over time. So more and more people actually do and show up and do designs. It was another interesting point when we tried another foundry. So you would have 40 slots in one manufacturing run and another one in parallel. That was a little bit of two parties at the same time. And it was overwhelmingly booked. Well, the booking here is a lottery. So how many people in the lottery was much larger than 45, which is 45 over 40 versus 90 or 88 over 40, and it keeps going. This was a little bit of fun, so we made sure that we do this on every chip. So if you do it and look at it in the microscope, you find that, and this is actually it was decapped and imaged by John McMaster, a community member who's doing these things just in his garage. And just many people have gotten into it, companies, as I mentioned, and universities and individuals. These are some examples of the work that's been done. And because we didn't say who does what, people came up with their own variety of applications. So, and then you can take a look at this, offline, but I encourage you to do that because you'll see the full design. This was an interesting one because you actually get the whole thing to work on a video. They developed an FPGA, and this is an FPGA with the software to implement what we're seeing here as a demo. So so this chip on here is an FPGA, but it's a small one. And people can, there are different, some people do radiation hardening designs, or they're not radiation hardening or extreme environment design can be done in either design or process. So people, we've seen great things, including what I mentioned here, Matt Ben. He created a course, that 0 to ASIC course. You've probably seen it. And but again, smaller designs, multiplexes, and they work, and it's kind of cool. If you want to go see a lot of these projects, just go to rehabs.com/projects. And again, forgive the different levels of documentation and coverage, but it's large number enough that you'll see and you'll actually learn from. Now, we found once this happened, people said, oh, I don't want to open source my design. I want to use these things. I don't want to have a lottery. And I want to go on my own schedule. So we created something called Chip Ignite at eFabless. And this is what brings me to the funding art. This is a commercial offering that brings the same technical offering that's in the program that was done, funded by Google. But it's actually, and the only reason I'm mentioning the numbers here is just because I spoke about funding in the title. So it's not like I'm trying to sell here in a sense, in a direct way. But just wanted to show that it is because of the optimization of the structures and making it the mask single tile and several things gone through to make that go to that price. And that price is not for area. So people compare this to say that compare it with other, how many millimeters do you have? Well, I'll say this is a 10 millimeters squares that have electricity and plumbing and a frame, and you get in and finish rather than just having an empty lot. You have to deal with it. So, and it's designed to also jump into low volume. And we're still, making that work even better. Now, if you calculate, so $20,000, you get 1,000 parts, that's $20. That's a very expensive proposition compared to a unit or a part that you buy for equivalent function. The only difference is actually it's your part. You can, and this is including all the masks and everything. There's no other costs. So the exercise of knowing the value is important. We did a bunch of options. People asked for a bigger design space. So, and there's a version of this, it's analog and digital. And again, it's the same interface. One of the things that actually led to the cost to be low, or the package is the same. So it's the same package, no change in package. Yes, less flexible, but if it's not working exactly, then it's not, that solution is not fit for you, but it solves it for a lot of other people. And then there's the IP. This is interesting because even though in the open source world, there's a lot of things that are going to happen, but we created a way to mix between the open source and not. So I'll tell you that the chip that Caravelle, there is a version that's coming out soon. It's ARM-based. So instead of a RISC-V core, it's an M0. And that was interesting because ARM wanted to do that, except it's not going to open source the design. Just the hardware is going to be available. The chip itself is going to be available, but anything you put in it, it's yours. And we're working on that library, and this is a community effort. So I will, if we talk offline, it's going to be call to action. Say, we need to, knowing that you can actually do it, we need to develop these things. Now, here's the twist. So after just full declaration, eFabless, Synopsys is an investor in eFabless, equity investor. How did that happen? How, what's the incentive? So because of the community of designers that are around us, it was very interesting proposition to say, as a company, Synopsys wanted to get ahead of that and said, I want to put my tools in the hands of the community as well. And now the open source EDA is considered a funnel opener. Many people can use it. Hundreds of thousands can use it. And then you can, if you want to have that option. The 5 minutes. So this is going to come in more news. It's going to come around it. We're going to be adding additional features for that, for Synopsys support. These are examples just for something we did with high school and a community college and for education's purposes. And just for the interest of time, these are all examples that are good and they were first time happening. One last thing here is that in this 5 minutes, I'll say, well, okay, it's still 10K. So I did the first campaign, and Josh held that against me and somewhere else, but it's called Clear. So I said, okay, let me start with that. So in literally like a couple hours, I said, okay, let's have this program where we're going to make a very small FPGA that's completely open source and call it Clear. And I wrote the page for it in a couple hours with some pictures and examples. And it wasn't overwhelming. It was intended to say, okay, I can actually come up with the money to make my own idea and fund it. It wasn't overwhelming funding, but it was funded. So now, if I didn't have the money, I can go crowdfunding, get market support or community support, and actually do it. This was done by eFabless itself. This one was done by another team, and it's actually, the chip is in the fab right now. Again, call them test vehicles because we're still starting, but I do encourage, and I think we're going to find good ways to work with crowd supply and making that even easier. And then you'll find examples, a lot of examples here. Twitter has been a rich medium to keep doing these things on them. And then, I'll keep that just to see what's going on around the community. This was a picture just I wanted to show. This is actually temperature testing for the board that because we wanted to have a complete setup with a camera that you can remotely actually play with it. And you can, take that chip for a spin, even if it's not. So.
Do you have plans for more than like 1,000 units?
Yes. So.
Is the pricing available online?
Not yet. So the threshold. So I'll tell you just a rough example. Like 10,000 is 130. So $13, and then you can keep going down. The threshold which it's going to make a difference, like if you're doing high volume, it's not going to make sense. Okay, so if you don't have high volume, you don't need this You don't need you have your solution. You don't need a. The good thing about this is that you can start and put it in the market and then see what picks. Yeah. So I think I'm done, at least for now, and then I can answer any questions now or through conversations. I'll be happy to. But the one message I'll give here is actually go do it. Go, as the slides are available, go to the github.com/efabless and get started. When I say get started, you literally clone a repo, run a make command, and you'll get an example from A to Z done in front of you that you can actually do it again and get your hands with it. And there's a lot of community support around it as well. So it is no longer an enigma. Just you can start and then modify from there. Thank you.